I am going to take an online course on theory and applications in thermal and cold plasma. So, this plasma, the term is almost known to all the students who are at least say 10th standard, 12th standard onward. Our sun is a plasma, the nature is having, if you ask anybody, they will say that more than 99% of the space is filled with plasma in the space. So that this is the kind of thing. Now, there are several courses on this plasma in books and also online available. But this course, this thermal and cold plasma, this particularly addresses the region where the plasma is actually being applied to the industry. You know that the your this plasma research is basically moving in uh, two ways. One is your fusion plasma and one is plasma activities other than the fusion plasma. Of course, both of them are interlinked and they are contributing or to each other. Now, the industry which are dealing with various applications of plasma, I'll come to all the details. So, that will be basically covered in this course. So, let me introduce myself. Myself is Dr. Sri Kumar Goroi, currently heading the thermal plasma technology sections of BARC, Trombay. I am also a professor at Homi National Institute. I am from 40th batch of training school. I did my PhD on this study of instabilities in arc plasma torches from the University of Mumbai. And then I did my postdoctorate from the high temperature plasma laboratory of University of Minnesota, Minneapolis. I basically worked on this plasma non-equilibrium CFD, plasma nonlinear dynamics there. And presently my area of interest includes arc instabilities, nonlinear dynamics, non-equilibrium CFD modeling, plasma device development, device fundamentals, and plasma chemistry and plasma processing. Actually, I do have work experience of more than 27 years in the field and teaching experience of 24 years. Basically, I am teaching at BSc Training School for quite long time. Also, I am teaching at the HBNI, this PhD courses. Now, basically, this course is originated from my work over last 27 years in the field of industrial plasma. As you can see that I started with developing a model of arc instabilities in plasma torches. That model is now not only confined to the field of plasma, it is now also being applied in other areas, other disciplines like chaos theory, control theory and all this. Then there is computational fluid dynamics. It is a very important part of this industrial plasma application or device design. The first non-equilibrium safety model of plasma cutting torches that I developed during my stay at the University of Minnesota. Then standard framework to calculate the thermodynamic and transport properties under the thermal equilibrium and non-equilibrium conditions. Also, I developed a robust code for doing these calculations, and it happened that this non-equilibrium properties actually what we computed, they are probably the first few which appeared in the literature. Then I obtained a new closed form analytical expression for charge-charge collision integral. Basically, when you want to calculate the properties of plasma, then you need to have the collision integrals. And as you know, this plasma is basically a collection of charged particles. So that necessarily need to include the collision between the charged particles. So that collision integral for this charge-charge interaction was not very easy to calculate, but we somehow got some a very closed form analytical expression, which are now being used by many people in this community. Then the dynamics of the plasma that is happening inside was very difficult to find out because of the very bright image, and it was very difficult to capture by camera. So we developed a way to find out how the plasma behaves internally, how the dynamics goes on. So probably that was the first time we were able to capture this kind of dynamics inside the arcs. Then there is a air plasma torch technology that you are seeing on the right side, upper right corner. So these are the plasma torches which are basically being used in the industry for various processing works, starting from management to plasma chemistry and many others. And this is a very important development. Why I will come to that in during my course, and I'll give you details of this device design and how one can work with different kinds of these plasma gases. That will be covered in the course. And then there is a new development where we are converting the air and water into nitrogen fertilizer. So we are able to develop a portable green technology for fast synthesis of nitrogen fertilizer for atmospheric air. And you know, it's both this technology, air plasma torch technology, and this nitrogen fertilizer synthesis from atmospheric air, both these technologies are given patent. One is granted and one is waiting. That has been applied. Then there is another application where we are very successful. It is the tunable cold atmospheric pressure plasma device. Basically, this tunability comes from some excitation frequency of high voltage. So depending on the frequency of excitation, the plasma behavior changes. And this plasma, unlike the thermal plasma, you can touch by hand, and it has many reactive pieces which can be used very meticulously for medical treatment. Like we have seen that it can selectively kill the cancer cells, leaving the healthy cells. So we have published all these results in various journal articles, as you can see here, and the device looks like this, as shown on the right side. Then there is one radio frequency plasma for synthesis of nanomaterials. You know, this technology is a very advanced technology to generate thermal plasma using radio frequency. As you can see on the right side, we are able to develop this device which can offer a large volume plasma, and that can be used for synthesis of various nanomaterials. Now, you know that we have developed these air plasma torches. Not only air plasma torches, we have developed almost all kind of torches which can be used for industrial scale plasma treatment. So one of them is plasma gasifier technology, where you can use the waste and generate gases which can be used in many different ways. So while application, I will come to this. Now, while I tell you about this industrial plasma research, that is the central theme of the course, the extent and the demand of expertise you can see in this slide. Starting from statistical mechanics, electronics, quantum mechanics, then sophisticated mathematics, then state-of-the-art optical and laser diagnostics, non-equilibrium thermodynamic and transport properties, then challenging numerical simulation, then of course the mechanical and electrical engineering, and study using nonlinear dynamics. So all this together actually describes the area of plasma research for industrial plasma technology. So as you can see that this course requires some basic knowledge about all these things. So, but this level of understanding, if you have up to say 12th standard, that is more than sufficient to proceed further with the course. It will not require any knowledge beyond the 12th standard to start with. So that will be sufficient to carry out this course. Now I come to the course, that theory and application in thermal and cold plasma. So in this first lecture, basically I am giving you introducing to the course, and this is basically the outline. With a crisp theoretical understanding at the beginning, the course will deal with device physics and process chemistries. This is very much required because you need to have a theoretical background to begin with. Then what we'll do, we'll together with the detailed understanding of the physics of plasma generation and thermophysical properties, we'll cover the most of the diagnostic techniques of industrial plasma. Then finally, we'll have a comprehensive understanding of some of the advanced technological applications in the area of industrial plasma. Now, who will be benefited from this course? Now, academic institutions offering advanced courses in industrial plasma technologies, large sector of medium and small scale industries and startups who wants to use plasma in their core processes. Then wide sector of medical research showing interest in plasma applications, they will be benefited, and the professionals in defense and space applications. So this course will basically make these professionals, students and medical practitioners fit to deal with the technologies that will appear or use the plasma technologies. To go with the course, the list of reference or books that you may consult, the first one is Introduction to Plasma Theory by Nicholson. This is a classic book. Whatever theory I will be teaching about the basic plasma physics, all of them you can get from this book. Then this Fundamentals of Plasma Physics by Bittencourt and Dendy and Chen. So they are all very popular books in the field of plasma, but most of them are oriented towards the very fundamental development of plasma physics, and orientation is mostly towards fusion plasma. Of course, industrial plasma is a part of that. So you can get more insight about the physics from these books. Then the fifth one, what I have given, this is a book on fundamentals of gaseous ionization and plasma electronics by Nasser. So this gives you a detailed idea of how you can use the ionization mechanism to produce the plasma, and different regimes of plasma, different types of plasma, how we can produce them. It is an excellent book on those things. Then comes to the diagnostics, as I was telling you. So this Hutchinson and a book by your Clam. So these are very good books on plasma diagnostics. So if you want to understand more about the various methods to diagnose the plasma, you can have from this. Then plasma, because of it is having lots of species who are very much reactive. For example, suppose you are using hydrogen. So normal hydrogen may not be very, very active. But the moment you go to atomic hydrogen, or ionized hydrogen or H2 plus. So this nascent and excited species becomes very very reactive, and those reactions which were not possible with ordinary hydrogen, they may be very much possible with the species generated by plasma. So plasma chemistry forms a very large sector of the studies that are being pursued in plasma, basically industrial plasma and application of plasma. Then there are two books on the last ninth and 10th. So there, one book is by Professor Boulos, Fouquet and Fender. So that is a very classic book. And on thermodynamic and transport properties, there is a last appendix in that, where from you can get readily available variation of these transport properties for equilibrium plasma. Then the 10th and 11th, these are applications of plasma technologies to material processing and plasma physics and engineering by Alexander Friedman. They're excellent book on this cold plasma areas. Actually, Alexander Friedman, you can say, among the very few people who has started this cold plasma activities and brought to such extent that now whole world is moving behind that. Then finally coming to the course actually. So this course is a 30 lectures course, and it starts with introduction to basic theory of thermal and cold plasma. So in this introduction, what we'll read actually, what is plasma, the four state of matter, then how ionization, recombination, diffusion, mobility in plasma works, the basic physics, then thermal ionization, Sa ionization equation, collective behavior, charge neutrality, space and time scales, plasma sheath, concept of plasma temperature, Debye length, plasma oscillation frequency, plasma parameter, criteria for plasma state, thermal and cold plasma, then collisions in plasma, small and large angle scattering, then collision-less approximations, equilibrium and non-equilibrium models, elementary concept of kinetic and fluid theory of plasma, and the image equations. So basically, this will introduce you to the fundamental theory, the elementary theory that will require to understand the course. As I told you that we don't need much prerequisite to start this course. 12th standard knowledge is sufficient, and from there you can build on. So in this very first 6 lectures will make you familiar with the fundamental requirement to understand what will be happening in the remaining of the course. Then in the second part, we will be going for these plasma devices, fundamentals and plasma generation in thermal and cold plasma. So it has 5 lectures, and we'll cover basic ionization physics and thermal plasma devices in this. So in the ionization physics, we will go through ionization potential of elements, ionization by electron collisions, Townsend's fast ionization coefficient, ionization by positive ion collision, photons, cathode processes, spanning effect, effect of contaminants, AC and DC breakdown, and Paschen law. So some of them, the concepts will derive, like the Paschen's law and how AC and DC breakdown differs, and if there is any contaminant, whether it can affect it, and how one can formulate the breakdown mechanism. In the thermal plasma devices part, we'll deal with this generation of thermal plasma, different techniques, designing a plasma torch, thermionic and thermochemical cathodes, desired features of the electrodes, power supply characteristics, discharge characteristics, transition from glow to arcs, arc characteristics, arc devices, design features, cathode and anode heat transfer, arc movement, inherent arc instabilities, cathode and anode jet formation, electromagnetic pumping, electromagnetic body forces, Jacobs plasma thrust. So these are the things that will be covered, and you will be very much enlightened that how these different mechanisms are being applied in the technological area. So we will explain all these things in this thermal plasma devices part. Then in the second part, we have 4 lectures of this topic. So here we will cover this radio frequency plasma devices, because in the class of thermal plasma, basically you will find that it is arc devices and RF plasma devices. We are covering the major part of the thermal plasma devices. So radio frequency plasma devices, they are basically sometimes called electrode less discharge. So when we want to have some plasma which are having extreme purity, then we go for this kind of plasma devices. Like in arcs, you need to have an electrode. Maybe it is of say tungsten, or maybe it is copper, or maybe it is hafnium. The moment it is in contact with the plasma, because of very high temperature, you know that the kind of temperature in thermal plasma they deal with can easily exceed 10,000s of degree Kelvin. At such high temperature, any solid material will get evaporated. Not only it will get evaporated, it will be ionized and it will form plasma. So this evaporated material has high potential to contaminate the plasma that is coming out, and if you are looking for a very high purity plasma application, then probably it is not possible with arc plasma devices. In that case, if you are using radio frequency plasma devices, you can have a very pure plasma, and this contamination issue may be completely resolved. So there is need of discussing in detail about these RF plasma devices. Then coming to the cold plasma devices, there are different devices has been developed which are operating in different frequencies like kilohertz, megahertz, radio frequency ranges different. And then there are dielectric barrier discharge, they are called DBD discharge, and there are charge coupled plasma, the direct discharges. So both of them can produce cold plasma. As I told you, here the plasma is so cold that you can touch it by hand really, and sometimes it is a bit higher, you can touch it by hand, but temperature is not very high, it is well less than 1000 degree Kelvin. So these cold plasma devices, different devices, how they work and what is the kind of plasma they generate, plasma characteristic, and what are the distinctive features of cold and thermal plasma devices, that will be discussed in this lectures. Then I coming to the Saha ionization equation and thermodynamic and transport properties in thermal and non-thermal plasma. So this is very important because you know whatever the plasma is having, what a plasma can offer you depends on the thermodynamic and transport properties of the plasma that you have generated. And this plasma can be generated in two forms. One is your thermal and one is non-thermal. So in case of thermal plasma, you have electrons and ion temperatures same, and in non-thermal plasma they are different. So depending on the type of species, their temperature, the transport properties will vary a lot. So how do they vary? How Saha ionization equation can help us to know about the plasma composition developed under a specific condition, under equilibrium and non-equilibrium conditions, that will be coming to know in these lectures. Then I will not go into the detail of thermodynamic and transport property calculation, but I will show in this lectures the hierarchy, that how you can obtain the thermodynamic and transport properties. So partition function hierarchy, then method to find plasma properties, elementary ideas on variation of these properties of common plasma gases, and their dependency on temperature, pressure, thermal and chemical non-equilibrium. I will not go into detailed derivation, but I will show you the physical behavior of these properties with temperature, pressure and non-equilibrium. Then coming to the diagnostics part, it will have 4 lectures and we will try to cover the emission spectroscopy and plasma process diagnostics. So how the emission spectroscopy is done? So the spectroscopic tools and plasma equilibrium, CT, LT and PLT concepts, because depending on that the spectroscopy technique will be different. Then the emission characteristics from your this thermal plasma and plasma in equilibrium and non-equilibrium, all these things will be coming out. Then what are optically thick and thin plasma, how the emission varies with them, and whether a plasma can emit like a black body. Then principles of level population, the quantum levels, then Boltzmann distribution, Boltzmann plot technique to determine the plasma temperature and their limitations, and how to determine the electron number density. So basically these are very elementary but very useful and very reliable techniques to understand how the plasma will behave and what is the type of plasma that you have generated using your device. Then coming to the process diagnostics, we'll see how we can conclude about the plasma that is generated through atomic and atomic and ionic emission lines, molecular bands, then how to identify the species, then how to get the idea about plasma particle interactions, and what are the tools to understand the temperature, velocity and density distributions of particles inside the plasma. Then Langmuir probe principles for finding the temperature and number density in cold plasma, and what are the limitations of every technique. So that will be knowing in this plasma diagnostic tools and principles section. And this is coming the last one, that is the emerging trends and novel applications of plasmas. We will be covering this part in 8 lectures, and basically we will be targeting the application of plasma technology for renewable energy and environments, then plasma in medicine, plasma in agriculture and plasma in synthesis of novel materials. So all these applications are very much interesting, and that is why we have kept a bit more lectures on this. And here in the plasma technology for renewable energy and environments, we will cover the plasma pyrolysis, gasification, incineration, waste to energy concept, electronic waste management and environmental application, and plasma cutting and welding. And in plasma in medicine part, we'll learn about the cold plasma application for cancer therapy, synthesis of nanocomposites, functionalization, targeted drug delivery, and etc. Then plasma in agriculture will come to know how the synthesis of nitrate fertilizer, seed germination, and plasma catalysis can help in the areas. Then for plasma synthesis of novel materials, this is a vast area and rapidly growing area, where we'll just get a flavor by knowing the activities in nanosynthesis, top-down and bottom-up approaches, homogeneous nucleation, unimodal and bimodal size distribution, size control principles, and plasma coating. So this is basically to get the basic ideas and how those principles are getting implemented in the technological part, that will be coming to know in this emerging trends and novel application of plasma part. So that completes the total of 30 lectures that we will be covering in this course, and we hope that we will be having a very enjoying session in the coming lectures. Okay, thank you very much.